Again, welcome to data mining course. In this lectures, we're going to explain the Weka output for classification or classified task. So in our previous lectures, we learned how to do classifies using Weka. Also, we went through this example, which is we use the ARIS data set, and we use our J48, which is the decision tree for Weka. So our main objective here is to explain the outputs of the results. The previous lecture again we explained, but we didn't go detail. And also here I will go through the definition of each of the outputs. So when we run our program here, the scheme will tell us what algorithm we use. So here we use the Weka classifiers, fall under the trees. In the trace section, we have different types of algorithm. Here we are using the J48. The relation tells us the file that we are using. The name of the file is ARIS. The instances tell us the number of records we have. In this case, we have 150 records. If it's customers, 150 customers. If it's patients, 150 patients. Here we have 150 different types of flowers measurements. So the instance of the flowers or the attributes, the characteristics of the attributes, which will be the, again, characteristics is the attribute of the instances or the records. We have 5. So for example, if it's a patient, one of the attributes or characteristics will be patient's ID or patient's last name or the patient weight, temperature, etc. But here again, we are dealing with flowers. The flowers, we have 4 main characteristics. Based on the measurement of the flowers, which is sepal length, sepal width, petal length, petal width, we can determine if the flowers is either Aris setosa, Aris vesicola, or Aris virginica. Those are the classes. So we have 3 classes. Now, how do we perform our classification process? As we said in the earlier lectures, we have 3 different options here to build our model and test it. Classification is normally 2 steps. First step, we have a training data. Training data means we also know the class already. So we have all the instances, we know the class. We use that training data to build a model. After we build the model finish, we are going to use a test set to test it and see how accurate or how precise the system is. So first, we can use a training set. Then we can also supply a test set. Or we can use the cross-validation process, which we went through in our previous lectures. Or the best way they are doing here, they are using the percentage rate, which means, again, the percentage is up to you can put any amount. For example, I can say, okay, in this data set, I'll use 50% of it to build a model. Then I'll use the other 50 to test the model. Here, they decided to use 66% to build a model. So that means the remaining 34% will be used to test the model. So that's what we have here. Test mode is 66% train, the remainder for testing. Now here they tell us we are using J48 and we develop our prune tree. This is the prune tree. Again, here we can visualize our tree. Well, I think we did that in our previous lectures. If I right-click, I can right-click on the items here, the trace J4848. Then I will see visualize option. Then I can visualize my tree. So the next section, again, this is continuation. That's why we use a red arrow. So I'm going to scroll down. When I scroll down, I'll get this section. So this is the most important section of the system, the output. First, we have correctly classified instances is 49, which is 96.0784%. Then incorrectly classified instances is 2. which is 3.9216. Total should be less than 100%. So here our kappa statistics is 0.9408. Kappa statistics normally tell us the model that we build, the result we get, is it by chance or is perfectly correct, actually. So if it's by chance, we get 0 or close to 0 value. And if it's perfectly did correctly, then it's by almost 1 or close. Here we get 0.9408, which is still good, almost 1 also. Then we have the mean absolute error, root mean square error, and relative absolute error. And relative absolute error, we can see that the value is more than 1. We will explain the reason why. We will go through the definition. Then the total number of instances, this is the testing section, it's 51. We will go through TP, stand for true positive rate, false positive rate. Precision was good, 1.905 for second, then the third. Recall Fmeasure. Then confusion matrix, as we said earlier, if we have a 2 by 2, it means our output is only 2 options. Like for example, a patient have a cancer, yes or no, true or false. So the dimension or the confusion matrix depends on the number of output. Here is 3 by 3 because we're expecting 3 possible result output. So we have aries setosa, aries vesicular, aries vaginica. Confusion matrix is very good because it correctly and also calculated show us the results. So we can see here, instead of saying, okay, let's say 49, that is 96.0%, let's say 96% of correctly classified. But confusion matrix will tell us which one was correctly or incorrectly classified. So when we look here, we have ABC. This is our possible 3 results, the target variable, aries setosa, aries vesicular, aries vaginica. So first we look at A, which is the aries setosa, and A 15. So that means correctly classified. The second row is supposed to be B, and all the B is 19. There's nothing in C, so that means 100% correctly classified. But when we come to C, which is aries vaginica, we have 2 at B, so that is incorrectly classified. So those 2 records showing that they are incorrectly classified, instead of aries vaginica, they went to aries vesicular because that's B. So again, and also from here, we can be able to determine the accuracy, precisions, or sensitivity, specificity, which we will go through. So first, let's go through the terms. So first, we have the relative absolute error. It's a way to measure the performance of a predictive model. Also, is the primarily used in machine learning, data mining, operations management. So relative absolute error is not to be confused with relative error, which is the general measure of precision or accuracy for instruments like clocks, rulers, or scales. Also, the relative absolute error is expressed as a ratio comparing a mean error residual to errors produced by trivial or naive model. So a reasonable model, one which produces results that are better than trivial model, will result in a ratio of less than 1. So you can see that in our result, relative absolute error was less than 1. We can check one more time. So relative absolute error, okay, here we have 7.1634, which is not too good. So here we say the relative absolute error is 7.1. Oh, sorry. Our result is 7. That's what I'm wondering. because if it's 7, which is very bad, but when we look at our result, it's very good result. 96% correctly classified is very perfect. It's very good. So it's in percentage. So our result is 0.07. So that's very good. Again, this is in percentage. The rest are in decimal value, but we have relative absolute error in percentage and also root relative squared error also in percentage, which means here is 0.34, which is still good also. So when we look at our result, or here they are all in zeros, which shows us that, I mean, it's less than 1, which tells us that the system is good. Now, if we should have 100% correctly classified, we should have get 0 for almost everything except the kappa statistics. Kappa statistics, remember, they say if it's 1, that means it's very good. Now, the result we get, the model we get, is not by chance. If it's 0 close to 0, then it's by chance. But here, 0.9 is almost 1, so it's not by chance. So now let's go through each definition. Next, we have the root mean square error. This is like a standard deviation of residuals. So standard deviation, residual will be an error. So for example, if this is very common in regression analysis. If I'm predicting something, I'll have the predicted value. If the predicted value is different from the actual value, the difference of it will give us what we call the residuals. And now when we get the residuals for all the items and we had, the total deviation will most likely give us 0. So sometimes we have to do it like finding the standard deviation, which means we are going to find a difference, each difference of the error. The error here is the difference of the actual value of y, let's say the output y, and also the predicted value of y. The difference of it we square. Then we add it to the next value again, the difference of the actual and predicted value all square. Now, if it's 0, it means the actual value and the predicted value are the same, and that's our main goal. So that's why we say when the root mean square error is 0 or close to 0, that's a good system. So residuals are the measure of how far from a regression line data points are, which is regression line is our predicted y values, and how far from it with the actual values. So it's a measure of how spread out these residuals are. In other words, it tells you how concentrated the data is around the line of best fit. So root mean square error is commonly used. Example can be forecasting is more common, and also regression. Very common in data mining, mostly regression and forecasting. We also have the root relative square error, which is relative to what it would have been if a simple predictor had been used. So more specifically, this simple predictor is just the average of the actual values. Thus, the relative square error takes the total square error and normalizes it by dividing by total square error of the simple predictor. Also, by taking the square root of the relative square error, one reduces the error to the same dimension as the quantity being predicted. And as we said in the kappa statistics, it takes into account the chance agreement, and also is defined as observed agreement minus expected agreement divided by 1 minus expected agreement. So when two measures agree only at a chance level, then the value of kappa is 0. When the two measurements agree perfectly, then the value of kappa is 1.0. We also have the confusion matrix, which is a technique for summarizing the performance of classification algorithm. So we saw our confusion matrix in Weka. Again, it shows the data that is correctly classified, the number of them in each category. So confusion matrix, again, as we said, The dimension depends on the number of output we have. In this case, our output is 3, so we have 3 by 3. But most of the time, we may get 2 by 2 a lot, especially when we are doing classification like decision trees. We may have, for example, as we mentioned earlier, for medical system, the diagnosis can be either positive or negative, or the testing may be. So in this case, we have 2 dimensions. Here we have 3 dimensions because we have aries setosa, aries vesicular, and aries virginica. And we can see how the confusion matrix is. From here, we can be able to find, for example, the concept of sensitivity, precision, etc. So next is the precision. Precision is defined as the number of true positive divided by the number of true positive plus the number of false positive. So from the confusion matrix, we can see the values for true positive, false positive, true negative, false negative, etc. So that's why we said again, from the confusion matrix, we can find the precision. Also, we have a recall. Recall will express the ability to find all relevant instances in the data set. So precision will express the proportion of the data point our model says was relevant. The proportion, or I'll say the percentage of the true positive. Whereas the recall, here we say it's called sensitivity also. It can be viewed as a probability that a relevant document is retrieved by the query. So example here, for a text search on a set of documents, recall is the number of correct results divided by the number of results that should have been returned. We also have what we call the F measures. We saw it in our classification output. And normally F measure, which is also called the F score in most statistics textbook, can be calculated based on the precision and also the recall. So based on the precision we have in recall. So the calculation is as follows. Precision equal to true positive divided by true positive plus false positive. We know the recall will be true positive over true positive plus false negative. Then F score will give us 2 times the precision times the recall divided by precision plus the recall. So we say that the score, the F score is considered perfect when it's 1, while the model is a total failure when it's 0. Remember that all models are wrong, but some are useful. That is, all models will generate some false negative, some will generate false positive, and possibly both. So this will be, again, the conclusion of our lectures. Now, when we go to the output again, we can see our Fs. So our F measure here, we can see we have almost 1. 1 for the class of aries setosa was perfect. 0.95 and 0.930, which is almost all the same perfect. But again, we know F measure is based on the recall and precision. So we can see that aries setosa, the precision and recall is perfectly 1. So that's why F measure is 1. You can see that. So that's why we said here again, let's go back one more time, that the F score is considered perfect when it's 1. And also the model is totally failure when it's 0. So the model will be created. When we look at this, all the scores again, it's very good model. First, we can see correctly classified is 96%. That's a lot. And also we can see the kappa statistics should be close to 1 or at least 1, which is correct. So it's perfectly, the result is not by chance. Then we can see all our errors are close to 0 or they are 0. 0.07, 0.3400. So again, I'm going to end the lectures here and wish everybody the best.